All right, so when you first take a look at this problem, and if you're like most of us, you start by jumping into A and reading A without reading anything else or really considering anything else. And we see, okay, when is F increasing or decreasing? And so you're probably thinking, okay, well that's easy. It's increasing in here and it's decreasing outside of that, but that's not the case. Because if we take a moment and read what else is going on here, notice the graph is the derivative f prime of x. This is not the graph of f of x, this is the graph of the derivative of f of x, and that changes things a decent amount. Alright, so knowing now that this is the derivative, we got to be thinking then about how does the derivative affect whether it's increasing or decreasing? Well, an increasing graph, if I were looking at the original function f of x, an increasing graph is anywhere where it's basically going uphill, so to speak. This is increasing. As I go to the right, I'm going up. Well, if that's increasing, what do we know about the derivative at every point on a graph that looks like this? It's above zero. It's positive. A positive slope means it's increasing. And so then if this is the graph of the derivative, then I'm looking to see that it's increasing anywhere where my graph is positive. And so then this would be increasing specifically on the interval from 0 up to 1. Notice it's not including it though, because at 1 it's 0. It's not positive anymore at 1, it's just 0. Okay, and then it is increasing again over here. And so we would also say it is increasing between 3 and 5. And that's it. All right, and then for the flip side, we need to see where is it decreasing. Of course, then that means that it would be decreasing anywhere where our derivative function is negative. So again, we have two different places where that's happening. So that's going to be between 1 and 3. And it's going to be between 5 and 6. So that's part A. That's when it's increasing or decreasing. Part B asks, when does it have a local maximum or minimum? Well, remember how we look for maximums and minimums. Those are the numbers at which the derivative equals 0. Because a maximum, it's going up and then it levels out, meaning the derivative is 0 at that maximum, and then it starts going down again. But notice what's happening there is that if it's a maximum, it was increasing and then it was decreasing. So I'm looking for the 0 that made the transition between increasing and decreasing. So if I take a look at this graph now, I was increasing here, I hit the 0, and then I was decreasing. And so then at 1 here, that means that must be a maximum. Because again, my slope was positive, then it was 0, and then it was negative. So it means that our graph hit a maximum. And specifically, a local maximum. All right, and then we can see the same kind of thing happening for the rest of these. So like at 3, it's decreasing, then the slope is 0, and then it's increasing. Notice what that forms. That forms a minimum. And so then I know that at 3, it's a minimum. And at x equals 5, notice it's behaving just like the first one did at 1, so that's a maximum. Because it's going from a positive slope to a negative slope. This is just a visual representation and discussion about what we're going to be doing basically throughout today. It's just using derivatives to think about increasing, decreasing, maximum, and minimum, that kind of stuff. So to start that, some notes. First notes is just this idea that a positive derivative, which means a positive slope, means it's increasing. And negative is decreasing. And then once we know this notes about the increasing, decreasing, then we can get formal about the local max and min as well. This is just a very formal way to write it out, of course. It's the same idea, it's just being very formalized. But we do need to take the formal notes as well, so go ahead and add this into your notes too. Right now, as you take a look at these notes here, just to make sure you understand what is going with what here, part A, f is changing from positive to negative. So that's like that first graph you see down below there. And so you notice that if it's changing from positive to negative, our slope is changing from positive to negative. So we were going up, and then all of a sudden we hit a point where we started going down. So obviously we must have hit the topmost point. So maximum. If you ever forget these notes, you can reason through to figure them out on your own that way. It's one of the nice things about this one. And then the opposite happens at B. So B happens, notice, when the slope changes from negative to positive. Well, so we're going to be going through some stuff, seeing how we can utilize that. But notice that whenever we make that change from negative to positive or positive to negative, when we make that change, what does the slope equal? 0. And so the derivative will equal 0 between them as well. And that's one of the things that we'll be taking a look at as we go forward. Then the last two graphs there, those are just examples of times when you'll see that kind of switch happening. They are C, part C from the notes there. Those last two graphs show where you don't necessarily always change from increasing to decreasing. You can go increasing, increasing in intervals. What that means there, as you can see, is it means that we get that 0 in the middle, that 0 slope, to show that it flattens out, but then it starts going up again. The most common graph that you would know that does this is x cubed. Because x cubed flattens out in the middle at that one point, and then it just keeps going up again. So then now we're going to practice this by just going straight from an equation and figuring out as we go. So go ahead and write down this problem, and then we'll work it together. Now for part A, it asks us when is it increasing or decreasing. Looking ahead to part B, it asks us about maximum and minimum values. All of those are going to be dependent upon the derivative. And so you're going to find that through basically this entire process, we're going to be working almost exclusively with the derivative. So step 1 here, go ahead and find out what is the derivative function. So figure out what f prime of x equals. And then once I know my derivative function, I want to know where are those places of change happening. In other words, where are the critical points? And so to find out where those critical points are, I want to know when this equals 0. So solve it for 0 equals. All right, and then in this case, we factor it in order to solve it. So now that I've factored it, I can know that the solutions are x equals 1/2 and -1. Those are the points of change. Those are going to be the dividing lines between my intervals. And so I can now start taking a look at what those intervals are going to be. So this one's including everything. So I'm going to go from -infinity up to the first of those critical values I just found. The first one is the -1. And then I go from the -1 up to 1/2. And then we go from the 1/2 up to a positive infinity. So those are the three possible intervals. Basically, I just took the whole -infinity up to infinity, and I broke it up on those lines. Wherever the solutions are, wherever it equals 0, those are the dividing lines. All right, so next up, I now need to figure out for each of these three intervals, every number within those intervals is either going to be positive or negative for my derivative. So I need to know, is it positive or negative for every number in there? And there's two different approaches you can take here. The first approach is that you can actually take a point within each of those intervals and plug it into our derivative function and see if it gives you a positive or negative. So like in this first interval, I could plug in -2, for instance. And I can plug in -2 over here, my derivative, f of -2. Does that give me a positive or a negative number? Well, it takes a bit of calculation, right? Well, when we do all of that calculation, you should end up finding that this gives us a positive. Now, I actually knew that before I even did the calculation because I know what this graph looks like, as do you. That's the other method you can use for this. Because I know that 12x squared plus 6x minus 6, it's a quadratic with a positive a value, so it's opening upward. And I know it crosses 0 somewhere in there. And so you notice it's positive on those ends, and then between my zeros, it's got to be negative. And so if you happen to know what the graph looks like, you can go ahead and use the graph because it's going to make your life a little bit easier. So I know they're negative in here, and they're positive here. Again, though, you can also find those values if you don't want to go the graph route. You can find them by just taking any point in that interval and plugging it in to see if it gives you a positive or a negative. And that's what they'll give you. All right, so that means that when the derivative is positive, it is increasing. When my derivative is negative, it is decreasing. And so then that takes care of part A. We've now identified the intervals on which it is increasing and decreasing. Now for part B, we're asked to find the local maximum and minimum values of the function. Well, remember that the maximum and minimum, those are the critical points. In this case, they just are the critical points. They're the points where it's 0. The derivative is 0 specifically. And so you can also see that as the points where you notice we stopped at -1 there, we stopped at 1/2 there. It's those points. You notice those, once I find these numbers, I use them for a couple different purposes. All right, so the maximum. The maximum, if you go back to your notes, you'll see that maximum is where our derivative changes from increasing to decreasing. And so it's basically going between these two intervals here. Notice that that hinged on the -1. And so it must be, the maximum must be at -1. The minimum is where we change from decreasing to increasing. Again, we can see that in our notes, or you can even reason it through, kind of visualizing, okay, if I'm going down and then all of a sudden I start going up, I must have bottomed out. And so my minimum then is at 1/2. Now those are actually my x values. I can go ahead and write my answer as a coordinate pair, so like I can plug those back in and see what those give us. So like for instance, if I take that -1, now notice I'm actually finding the y value of the actual original graph. So I plug the -1 now into the original function, do f of -1. So when I plug that in, I get a y value of 6. So that's the actual coordinate pair where the maximum occurs, the local maximum. This one has no absolute maximum because if I looked at the original graph, I'd be seeing something that looks more like this. It goes up to infinity. Now for the minimum, I again would plug 1/2 into the original function. So we'd figure out what is f of 1/2. And we plug that in, we get -3/4 to see that's where the minimum occurs. And so there's our answers. Having just done that one, I think you can now go ahead and do this problem on your own, because it's basically the same kind of process. So let's see how well you have that whole process down. Work it through first, and then we'll go through it together. Hopefully the first thing you're doing is finding the derivative function. And then once you know the derivative function, set it equal to 0 and solve for x. This one isn't too bad to solve because it does factor into 4x squared times x minus 3. So you should find that x equals 0 and 3. So those are your critical points here. And so once I have those x values of 0 and 3, I take the whole -infinity to infinity and I break it up along those numbers to create those intervals. All right, and so then I want to figure out, is my derivative positive or negative within each of those intervals? And so, like, since I don't know what the graph looks like instantly off the top of my head, I'm going to go ahead and grab a point that's within that first interval. So I'm going to use -1. And I'm going to plug that into my derivative function. If I plug -1 in there, notice I end up doing a -4 minus 12. That gives me a negative number. And so that's negative in that interval. I can repeat the process with the next two intervals as well. For the second interval, I might grab a number in there like 1. 1's a nice easy number to plug into the derivative. If I plug 1 in there, I end up doing 4 minus 12. That also gives me a negative. So yes, you can have consecutive intervals that both have the same sign. That's kind of like the example that we saw earlier, where it might be looking like this, sort of a graph. And that actually is what it's doing within that portion of it at least. And then we grab a point out of the last interval, like you might grab 4 out of that last interval. Plug it into the derivative function, because I want to know if the derivative is positive or negative. And in this case, you end up getting a positive number. And so now we can know when it's increasing or decreasing. So it's decreasing on both of those intervals. And it is increasing on that one interval. So now we've answered the questions from part A. Now for part B, it asks us to find the local maximum and minimum values of the function. All right, and so then for part B, to find the local maximum, remember from our notes, that is when we transition from a positive slope into a negative slope. Or in other words, we are going from increasing to decreasing. Well, you notice up here that never happens. We never go from an increasing situation to a decreasing situation. And so there actually is no maximum, no local maximum in this problem. The minimum, well, from our notes, we know that's where it goes from decreasing to increasing. And so I look up there to see where that happens, and that does happen. That happens across the 3 here. And so since it happens at 3, then I know my minimum is going to be where x is 3. And I can plug that back in to find out what the y-coordinate is so I can get the actual point of the local minimum. And I get 3, -27. Remember that I get this -27 here by plugging the 3 into the original function, because the 27 is the height of the point, not its slope like derivative would tell me. And one other thing that's kind of cool about this is that, do you see how actually this information is enough to tell you what the graph looks like? Because if I know that from 0 or from negative infinity up to 0 that it is decreasing, I can go ahead and start making my graph decreasing. And then at 3 it's 0, so I know it's leveled out there. But then it goes decreasing again. So now I can go ahead and pick it up going down. And then it transitions to increasing. And so I can actually see a very rough idea about what this graph looks like. All right, so this is the last one we're going to be doing together here. But the process will be the same. Just we'll have to deal with some of the trig stuff that comes along the way, unit circle values, stuff like that. So for this one, start working it through. If you get stumped somewhere along the line, hold there. But at least work through it as far as you can before we start going through it together here. All right, so for this problem, first of all, one little subtlety to note. Notice that I can use these same techniques on a restricted interval. So I can do it just over this domain. It doesn't have to be for all real numbers, which is nice considering that for sine or cosine, we could end up with infinite numbers of solutions if we didn't restrict it. All right, so we want to know when it's increasing or decreasing. The first thing I need to do then is find the derivative function, because everything we do is going to be dependent upon that derivative function. So we go f prime of x equals 1 plus 2 cosine of x. Now the first thing I use that for is to find out when the derivative equals 0. And so we go ahead and solve it for 0. So that means 0 equals 1 plus 2 cosine of x. I subtract the 1 from both sides and then divide by 2. So I'm looking to see when we get a -1/2 for cosine of x. And at this point, you have to remember your unit circle. And so if we kind of envision our unit circle here as a way to solve this, because yes, visualization is a great way to do it, I'm looking to see when cosine is negative 1/2. Now if you're rusty on your unit circle, the first thing to remember is cosine. Is that how far we go over or how far we go up? Cosine is how far we go over, yes. And so I want that to then be a negative 1/2. So I'm looking basically for those values. Now, the negative 1/2, that's about the smallest number I could go over. Because root 2 over 2 is even further out. Root 3 over 2 is even further than that. So that means it's a fairly steep angle here where it's going to happen. And so then we can kind of get our head around where it is. Specifically, in this case, you might have to work the angles in different ways to remember. That's kind of an individual thing in terms of how you remember that these are what the angles are called. It ends up giving us x equals 2 pi over 3 and 4 pi over 3. All right, now that we've found our solutions, now we can go ahead and look at our intervals that we're actually going to work with. So for our intervals here in this case, remember that we're on a restricted domain, so the first thing I'm going to start with then is the 0. And I'm going to go from 0 up to the first of the critical numbers, which was the 2 pi over 3. And then the next one, 2 pi over 3, is going to go up to 4 pi over 3, because both of those are in fact between 0 and 2 pi. And then that means the last one then is going to go from 4 pi over 3 up to the 2 pi. All right, now we want to know for every single point within each of those intervals, is my derivative positive or negative, in order to know if it's increasing or decreasing. In order to do that, you got a couple different options. Probably depends on how well you know your unit circle. Because for me, I know my unit circle pretty well. Not surprising, right? I'm a math teacher, for crying out loud. But because I know my unit circle really well, I know that within that interval is a nice, easy point to figure out cosine. Pi over 2. And so I could take that pi over 2 value and plug it in for x here, and I know that cosine of pi over 2 is 0. 2 times 0 is 0. 1 plus 0 would be 1. It gave me a positive number, so I know it's positive in there. Or the other method you could use is actually a graphing one, because we know what the graph of this derivative function would look like. Because remember, I'm just considering what the derivative is. I know it's a cosine graph, so it'd start at the top. And so I know it's doing one of those. And within there, I know that these are my zeros. And so I can see that it starts positive, then it goes negative, and then it goes positive again. Or you can go ahead and just test numbers within them. Up to you. Either way you do it though, you should end up finding the same set of increasing and decreasing. So it's increasing on the interval 0 to 2 pi over 3 and 4 pi over 3 to 2 pi. And it's decreasing from 2 pi over 3 to 4 pi over 3. Knowing that is now allowing me to do part B, where I find the local maximum and minimum values. Because remember that a local maximum occurs anytime we are going from a positive derivative to a negative derivative. Well, that does happen in this case. That happens right in here. Our transition point, the 0 between them that we used, was 2 pi over 3. So the maximum occurs when x is 2 pi over 3. Yes, I could plug that back into the original function up here and figure out what the y value is as well. I'm just not going to worry about going through that step at the moment. And then we go through the minimum. And so for the minimum, that's where we transition from negative into a positive slope derivative. Remember, it's all about the increasing, decreasing. And so we can see that happening going from here to here. That happens across the number 4 pi over 3. And so that's where the minimum is. It's going to be at 4 pi over 3.